So we again want to find the upward flux of the same radial field, which is xyz, but now we're going to look at it across the portion of the cone, which is z equals the square root of x squared plus y squared. Now I have this drawn in maple for us to look at. So you can see the cone, you can see the vector field is sitting all around the cone, or if you will, the cone is sitting inside the vector field, and it casts a shadow onto the xy plane. That's our region of integration. Now, where is that shadow? Well, we find the intersection, which would be z equals the square root of x squared plus y squared, and z equals 2. So we set the square root of x squared plus y squared equal to 2. Therefore, x squared plus y squared is equal to 4. And we're probably going to go polar because it's a circle. So r squared is 4, so r is 2. All right, so our region of integration, oh, I should have said, this is the surface up here. And then down here will be our region of integration. Okay. So now we need to find a whole bunch of stuff so that we can actually run this integral. So we're going to need, oh, and let me just label this surface. The surface is z equals the square root of x squared plus y squared. And if we do go polar, which we will, that's z equals the square root of r squared, which is r. All right, now let's put a line down and then let's start working on all the pieces that we're going to need to be able to find this integral. For starters, we need to find our normal vector. To do that, we have to take the z of xy and turn it into w. W equals z minus z of xy, which would be z minus the square root of x squared plus y squared. I should mention, we're doing upwards and downwards because this is z. If you wanted left and right flux, you would define the function in terms of y. And if you want front and back, you would define the function in terms of x. Remember that when we first had this formula, it said that we could modify the surface as needed. So if you needed to go in a different direction, that's how you would do it. All right, because we want upward, we want the z in front, and this is going to work because that'll give us 1 for the derivative when we get there, which is what we're about to do. So the normal vector is the gradient of w. That's wx comma wy comma wz. All right, so just like with the last one, this is to the 1/2 power, really. So we bring the half down, so it's negative 1/2 x squared plus y squared to the negative 1/2 times 2x. And then same thing for the other one, negative 1/2 x squared plus y squared to the negative 1/2 times 2y. And then it's 1, which shows the upward portion. So those pieces put together make it upward. Okay, so let's simplify that just a little bit before we have to head on. So that would be the 2 and the half would cancel, be negative x over the square root of x squared plus y squared, and then negative y over the square root of x squared plus y squared. This is looking familiar. It's very similar to the last one. And then 1. All right, so there's our normal vector. It's not pretty, but there it is. All right, so now we need to find our force vector, or excuse me, vector field. So the vector field, which was x, y, z, is no good to us. We can't use z, so we have to eliminate z. All right, well, we know that z is the square root of x squared plus y squared. So we could say this is x, y, the square root of x squared plus y squared. Just like that. All right, now again, as in the last problem, we have to choose when we want to switch over to polar. We can tell that we want to. So it's just a question of, do we do it now or do we do it later? So in the last problem, I actually did it later. So I did the algebra with the x's and y's, and then I figured out the polar. But it doesn't have to be that way. I could actually do it right now. I just need to give myself a little room here. So this would be, let me rewrite this one in polar, the normal vector, that is. Actually, I don't have room up there. I'm going to have to just make a note here. I'm going to rewrite n and f in polar right now. Again, you don't have to do it right now. I mean, you're going to do it eventually, so it's just a question of when. So the normal vector would become negative r cosine theta over the square root of r squared, which is r. And then negative r sine theta over the square root of r squared, and 1. So that's just going to be negative cosine of theta over, or excuse me, negative cosine of theta. The r's would cancel because this is the square root of r squared, which is r. So it's negative cosine of theta, negative sine of theta, and 1. As for the vector field, f, that would be r cosine theta, r sine theta, and the square root of r squared, right? So if you go polar, this is r squared. And the square root of r squared is just r. So in the last problem, I did it later. In this problem, I'm doing it earlier. I could have done it earlier in the last problem as well. I just wanted to show you both possibilities. Okay, so now we're going to actually find the flux. So that's going to be down here. Okay, so remember that flux is the double integral over the region of f times n dA. Okay, so flux is the double integral over, okay, f is now r cosine theta, r sine theta. Oh, I meant to write 1 there. I don't know what I was doing. Oh, no, it is r. Sorry, it's this one that's 1. That's r. R. There we go. And then I'm going to dot product that with the normal vector, which was, this is the one with the 1, negative cosine of theta, negative sine of theta, 1. And then because of I'm switching to polar, I'm going to put r dr d theta. Now what about r and theta? I didn't bother to find them, but they're obvious. R goes from 0 to 2. Theta goes from 0 to 2 pi. Standard issue. So we go 0 to 2 pi and 0 to 2. So I'm going to write 0 to 2 pi, 0 to 2, and then I'm going to multiply these. So this is negative r cosine squared, and then minus r sine squared, plus r, and all of that's times r dr d theta. Well, if you're paying attention, you might realize there's something going on here with this one. If I factor a negative r out, I'm left with cosine squared of theta plus sine squared of theta, and that is 1 by the Pythagorean identity. So this whole thing becomes negative r plus r. So this is the double integral from 0 to 2 pi, 0 to 2 of negative r plus r times r dr d theta. And negative r plus r is 0. So we're integrating 0. And the integral of 0 is 0. Right? 0 times r is 0. So this whole thing is 0. Now, what in the world? Why is that happening? Well, look back at the graph again. Let's come back. So the question is, how much are the vectors, the arrows, poking out and crossing over that cone? And the answer is they're not. They're going right with it. Look at that. They line up perfectly. They're not crossing. They're all in the same direction, if you will, as the cone. They're not crossing it at all. That's why there's no flux. This cone sits inside that vector field in such a way that none of the vectors actually pass over or pass through the cone. And that's different from the previous example. So in the previous example, it doesn't have a ton of flux, but you can see the arrows are not lining up perfectly. Here, let me try to get them lined up. They don't line up perfectly, right? It's pointing towards the surface, then it's crossing over, right? So that's not perfect the way that the other one is. So if you line up this one, those arrows line up perfectly. They don't cross the surface at all. So that's what's happening. So there's no flux because the vector field does not cross the surface. It goes with the surface. So that's what I wrote right there. Right? We don't have any flux because that vector field's never crossing the surface. It's actually just kind of flowing along with the surface.